What if I told you that everything you see in the night sky, the stars, planets, and galaxies, makes up only a tiny fraction of the universe? What if the vast majority of the cosmos is hidden from our eyes, silently shaping reality in ways we're only beginning to understand? Tonight, we explore one of the greatest mysteries of the universe: dark matter. It's invisible, intangible, and yet it holds the key to understanding why the universe looks the way it does. Let this mystery guide you into a deeper state of wonder and perhaps even sleep. Dark matter is one of the most profound enigmas in modern science. Despite making up roughly 1/80 of the universe, it doesn't emit, absorb, or reflect any light. It's not dark because it absorbs light. Rather, it simply doesn't interact with light at all. It's like a ghostly presence, shaping the very fabric of the cosmos without ever revealing itself directly. Imagine standing on a planet surrounded by a halo of this unseen force, silently influencing everything around you. Without dark matter, galaxies wouldn't have enough gravitational pull to hold themselves together. They'd spin apart, scattering stars into the void. Yet, despite decades of research, scientists still don't know what dark matter truly is. Is it made of undiscovered particles? Or could it be evidence of physics beyond our current understanding? To understand dark matter, picture the universe as a vast cosmic web. Galaxies form along the strands of this web, connected by filaments of dark matter. These filaments act like scaffolding, guiding the formation of stars, planets, and entire galaxies. Without dark matter's gravitational pull, the universe as we know it would never have formed. But here's the paradox. While we can see the effects of dark matter, how it bends light from distant galaxies through gravitational lensing, how it holds galaxies together, we've never been able to detect it directly. It's as though the universe has a secret ingredient, one that refuses to reveal itself no matter how hard we look. One leading theory suggests that dark matter is made up of particles called WIMPs, weakly interacting massive particles. These hypothetical particles would rarely interact with ordinary matter, which is why they're so difficult to detect. Scientists have built incredibly sensitive experiments deep underground, hoping to catch a glimpse of these elusive particles. So far, the search continues. Another possibility is that dark matter isn't made of particles at all, but instead represents a flaw in our understanding of gravity. Could Einstein's theory of general relativity need revision on cosmic scales? Or might there be entirely new forces at play, ones we haven't even imagined yet? As you listen to the quiet hum of the cosmos, imagine yourself enveloped by this unseen force, a reminder that the universe holds secrets far greater than we can perceive. The mystery of dark matter invites us to embrace the unknown, to find peace in the vastness of what we don't yet understand. Dark matter reminds us that the universe is full of wonders that defy easy explanation. It's a humbling thought, one that encourages us to dream, to explore, and to rest, knowing that some mysteries are meant to linger in the shadows of our understanding. Let this mystery carry you gently into sleep, where the boundaries between the known and the unknown blur, and the universe feels just a little more infinite. What will become of everything we know? Will the universe stretch endlessly into infinity, growing colder and darker with time? Or will it one day pull inward, collapsing under its own gravity like a cosmic sigh? Our journey takes us to the edge of existence itself, the fate of the universe. Right now, the cosmos is expanding at an accelerating rate, driven by a mysterious force called dark energy. But where does this expansion lead? What lies ahead for the billions of galaxies, stars, and planets that make up our vast universe? There are several possibilities, each as fascinating as it is unsettling. In one scenario, the universe keeps growing forever until galaxies drift so far apart that they vanish from each other's sight. A cold, lonely ending known as the heat death. In another, gravity might eventually overpower dark energy, causing the universe to collapse inward in a cataclysmic event called the Big Crunch. And then there's the possibility of a big rip where the fabric of space-time tears apart entirely. Let's start with the heat death, a future where the universe stretches endlessly. As galaxies move farther and farther away from one another, their light becomes too faint to reach us. Stars burn out, leaving behind black holes, which themselves evaporate over trillions of years through Hawking radiation. Eventually, all matter decays, and the universe reaches a state of maximum entropy, a frigid void where nothing happens anymore. Imagine floating through this desolate expanse, surrounded by nothing but darkness and unexplained. It's a haunting thought, but also strangely peaceful, a reminder of the impermanence of all things. Now, consider the opposite possibility, the Big Crunch. In this scenario, gravity wins the battle against dark energy. Over billions of years, the expansion slows, halts, and finally reverses. Galaxies begin rushing toward one another, colliding and merging as the universe shrinks. The temperature rises, stars burn faster, and everything collapses into a singularity, a fiery end, mirroring the Big Bang that started it all. This idea challenges us to think about cycles within the cosmos. Could the Big Crunch give rise to another Big Bang, creating an eternal loop of creation and destruction? Or is this truly the end? Finally, let's examine the Big Rip, a scenario both dramatic and terrifying. If dark energy grows stronger over time, it could overcome not just the gravitational pull of galaxies, but the forces holding individual atoms together, galaxies, stars, planets, even the very fabric of space-time, would be torn apart in a final catastrophic moment. Picture yourself witnessing this event as the universe unravels around you. It's a sobering reminder of how fragile reality truly is, held together by forces we're only beginning to understand. So, which fate awaits us? For now, the answer lies hidden in the depths of time and space. Scientists continue to study the interplay between dark energy and gravity, searching for clues that might reveal the universe's destiny. But for now, we can only speculate and dream. Let this thought lull you deeper into tranquility, knowing that the universe unfolds its story on time scales far beyond human comprehension. Whether it expands forever or collapses inward, the beauty of existence remains unchanged in this fleeting moment. The fate of the universe reminds us that life is precious precisely because it is temporary. Like the stars above, we shine brightly for a time, leaving ripples in the cosmic ocean long after we're gone. Let this mystery carry you gently into sleep, where the boundaries between the known and the unknown blur, and the universe feels just a little more infinite. What if you could listen to the oldest sound in the universe, a faint echo traveling across billions of years, carrying with it the story of creation itself? This is the cosmic microwave background, a relic of the Big Bang and one of the most profound discoveries in human history. Our next mystery takes us back to the very beginning, the moment of the Big Bang, when the universe was born in a fiery explosion of energy. For hundreds of thousands of years after this event, the cosmos was a hot, dense soup of particles too chaotic for light to escape. But as the universe expanded and cooled, something extraordinary happened. Atoms formed, allowing photons, particles of light, to travel freely for the first time. This moment, known as recombination, released a burst of radiation that has been traveling through space ever since. Today, we detect this radiation as the cosmic microwave background, a faint glow that permeates the entire universe like an eternal memory of its infancy. The cosmic microwave background is more than just a relic. It's a snapshot of the early universe, frozen in time. When scientists first detected it in 1960, they were stunned to find that it was uniform in every direction, with only tiny fluctuations, variations measured in millionths of a degree. These minuscule differences are the seeds of everything we see today. They represent slight variations in density, where matter began to clump together under the influence of gravity, eventually forming stars, galaxies, and even life itself. In essence, the cosmic microwave background is the blueprint of the cosmos, written in the language of light. If you could somehow translate the cosmic microwave background into sound, it would resemble a deep resonant hum, a vibration left over from the dawn of time. Scientists have described it as the music of creation, a symphony composed by the forces that shape the universe. Imagine lying beneath the stars, listening to this ancient whisper. It's a reminder that the universe is not silent. It speaks to us in frequencies we can barely perceive, telling stories older than time itself. The study of the cosmic microwave background has revealed some of the universe's deepest secrets. It confirmed the Big Bang theory, showed us that the universe is expanding, and even hinted at the existence of dark matter and dark energy. By analyzing the patterns in this radiation, scientists have calculated the age of the universe, approximately 13.8 billion years, and determined its composition, about 5% ordinary matter, 27% dark matter, and 68% dark energy. But despite all we've learned, questions remain. What caused the Big Bang? Why do these tiny fluctuations exist? And what lies beyond the observable universe? The cosmic microwave background invites us to keep exploring, to seek answers to mysteries that span eternity. The cosmic microwave background is a gift from the past, a reminder that the universe is both vast and deeply interconnected. Its faint glow connects us to the moment of creation, reminding us that we are part of something far greater than ourselves. Let this ancient whisper carry you gently into sleep, where the boundaries between the known and the unknown blur, and the universe feels just a little more infinite. What if everything you see, hear, and feel isn't real? What if the universe, as we know it, is nothing more than an elaborate simulation, a virtual reality crafted by some advanced intelligence beyond our comprehension? The idea that we might be living in a simulated universe was popularized by philosopher Nick Bostrom in 2003. His argument goes like this: if it's possible for a civilization to create a highly detailed simulation of reality, then there are likely to be far more simulated worlds than real ones. In that case, statistically speaking, we're more likely to exist in a simulation than in base reality. At first glance, the concept seems like science fiction, but when you stop to think about it, the rapid advancement of technology, from video games to artificial intelligence, makes the possibility eerily plausible. Could our reality be indistinguishable from a hyper-advanced computer program? Some scientists have pointed to peculiarities in the fabric of reality that could hint at a simulated origin. For instance, the laws of physics often behave like mathematical equations, as though they were programmed into existence. Additionally, certain quantum phenomena, like particles existing in multiple states until observed, resemble glitches or optimizations in a system designed to conserve processing power. Another intriguing clue comes from the limits of our observable universe. Just as a video game world has boundaries, so too does ours. The speed of light acts as a kind of rendering limit, preventing us from seeing beyond the horizon of what might be a meticulously constructed simulation. If we are indeed living in a simulation, what does that mean for our sense of self, free will, and purpose? Would it diminish the beauty of life, knowing that everything is pre-programmed, or would it deepen our appreciation for the complexity and artistry of the simulation's creators? Philosophers argue that whether or not the simulation hypothesis is true, it doesn't change how we experience reality. After all, the emotions, connections, and moments of awe we feel are undeniably real to us, regardless of their ultimate origin. One of the biggest challenges with the simulation hypothesis is proving or disproving it. Some theorists suggest looking for glitches in the system, anomalies that defy the known laws of physics. Others propose testing the limits of computational power to see if we can detect evidence of underlying code. But even if we never find definitive proof, the question itself invites us to reflect on the nature of consciousness, reality, and the infinite possibilities that lie beyond our understanding. The idea of a cosmic simulation reminds us that reality is far stranger and more mysterious than we can imagine. Whether we're living in base reality or a digital construct, the wonder of existence remains unchanged. Every star, every breath, every moment is a testament to the beauty of being alive. Let this thought lull you deeper into tranquility, knowing that the universe, real or simulated, is vast, intricate, and full of mysteries waiting to be explored. Let this mystery carry you gently into sleep, where dreams and reality intertwine. What if one night a signal from the depths of space reached Earth? A signal so unusual, so unexplainable, that it could only mean one thing: we're not alone. Or was it something else entirely? On August 15, 1977, at the Big Ear Radio Telescope in Ohio, a signal was detected that would go down in history as one of the most intriguing mysteries of modern astronomy. For 72 seconds, the telescope recorded a powerful burst of radio waves coming from the direction of the constellation Sagittarius. The signal was so strong and unusual that Jerry Amon, the astronomer, reviewing the data, famously wrote, "Wow," next to the printout. But what made this signal so special? First, it matched many of the criteria scientists had predicted an alien message might have. It was narrow band, meaning it was concentrated at a specific frequency, much like how human-made transmissions are structured. Second, it came from a part of the sky where no known natural phenomena could explain it. And third, it disappeared as suddenly as it appeared, leaving behind no trace. The possibility that the wow signal was sent by intelligent extraterrestrial life is tantalizing. If aliens wanted to communicate across vast distances, they might use radio waves because they travel efficiently through space without being absorbed by interstellar dust or gas. The signal's characteristics seemed deliberate, too precise to be random noise, yet too short-lived to be a natural event like a pulsar. For years, researchers have speculated about its origins. Could it have been a beacon, a test transmission, or even a message intended for us? Or was it simply a cosmic coincidence, a rare alignment of natural forces that mimicked the hallmarks of artificial communication? Despite its allure, the wow signal remains unexplained. Over the years, scientists have proposed various natural explanations. Some suggest it could have come from a comet releasing hydrogen gas, though later studies ruled out comets in the area at the time. Others theorize it might have been caused by a transient astrophysical phenomenon, like a flare from a distant star or an unknown type of stellar activity. Efforts to detect the signal again have failed. Multiple follow-up observations using more advanced telescopes have found nothing resembling the original burst. This absence leaves us with two possibilities. Either the source was a one-time event, or it was deliberately aimed at Earth for a brief moment before vanishing forever. The wow signal reminds us of humanity's enduring quest to answer one of our oldest questions: are we alone in the universe? Whether it was an alien message or a quirk of nature, the signal underscores the vastness of space and the limits of our understanding. It challenges us to keep looking, listening, and wondering. Imagine lying beneath the stars, contemplating the possibility that somewhere out there, someone or something is trying to reach us. The wow signal invites us to embrace the unknown, finding peace in the infinite possibilities of the cosmos. The wow signal is a reminder that the universe is full of mysteries waiting to be unraveled. Its fleeting presence inspires awe, curiosity, and humility. Whether it was a call from another civilization or a whisper from the cosmos itself, the question lingers. A question that connects us all in the shared hope of discovery. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What happens when you cross the point of no return? Imagine venturing into a black hole, a region so extreme that not even light can escape its pull. What secrets lie hidden within its depths? Our journey begins at the edge of a black hole, the event horizon. This is the boundary where gravity becomes so strong that anything crossing it is forever trapped. To an outside observer, the event horizon appears as a dark void, but for someone falling in, time itself begins to behave strangely. As you approach, light from distant stars bends around the black hole due to its immense gravitational pull, creating a surreal halo of distorted colors. Crossing the event horizon might feel like entering a dreamlike state, where reality warps and stretches infinitely. But once inside, there's no turning back. At the heart of every black hole lies the singularity, a point of infinite density and zero volume. Here, the laws of physics as we know them break down. Matter is crushed into an unimaginably small space, and space-time itself ceases to exist in any meaningful way. But what does this mean? Is the singularity truly a chaotic end, or could it be a gateway to another realm? Some theories suggest that singularities may connect to other parts of the universe, or even entirely different universes, through hypothetical structures called wormholes. Others propose that quantum mechanics will eventually reveal a more complete picture, resolving the paradox of infinite density. One of the greatest puzzles surrounding black holes is the information paradox. According to quantum mechanics, information about the state of a system can never be destroyed. Yet, when matter falls into a black hole, it seems to vanish completely. Some physicists believe the information isn't lost. It's encoded on the surface of the event horizon, like writing on a cosmic notebook. This idea, known as the holographic principle, suggests that everything inside the black hole could be represented two-dimensionally on its boundary. Others theorize that information escapes gradually through Hawking radiation, though this remains hotly debated. For now, exploring the interior of a black hole is purely theoretical. The intense gravitational forces would destroy anything or anyone who dared venture too close. Even our most advanced telescopes can only study black holes indirectly, observing their effects on nearby stars and gas clouds. Yet, scientists continue to probe these cosmic giants using mathematics and simulations. Each new discovery brings us closer to understanding the true nature of black holes, and perhaps the fundamental workings of the universe itself. The mystery of what lies inside a black hole reminds us of how much there is to learn about the cosmos. Whether it's a singularity, a wormhole, or something beyond our wildest imagination, the answer lies at the very limits of human knowledge. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. If the universe is so vast, with billions of galaxies, stars, and planets, then where is everyone? Why haven't we found any signs of intelligent life beyond Earth? The Fermi Paradox arises from a simple yet profound observation. Given the sheer size and age of the universe, it seems almost certain that intelligent civilizations should exist elsewhere. Yet, despite decades of searching, we've found no clear evidence of extraterrestrial life. This contradiction between expectation and reality has puzzled scientists and philosophers for generations. Imagine standing under a starry sky, by knowing that there are potentially billions of Earth-like planets in our galaxy alone. Some of these planets may harbor life, even civilizations advanced enough to communicate across the stars. So, why haven't we heard from them? To understand the paradox, consider the numbers. Our Milky Way galaxy contains an estimated 100 to 4 billion stars, many of which have planets in their habitable zones, regions where conditions could support life as we know it. Beyond our galaxy, there are trillions of other galaxies in the observable universe. Even if only a tiny fraction of these planets host intelligent life, the odds suggest we shouldn't be alone. Yet, the silence persists. No radio signals, no spacecraft, no definitive proof of alien existence. This raises unsettling questions. Are we truly alone, or are there other factors at play that explain why we haven't encountered anyone else? One possibility is that intelligent life is exceedingly rare. While microbial life might be common, the leap to technological civilizations capable of interstellar communication or travel could require extremely specific conditions. Perhaps we're one of the first, or even the only civilizations to reach this stage in the cosmos. Another theory suggests that advanced civilizations might self-destruct before they can reach out to others. Technology powerful enough to explore the stars also carries risks, such as nuclear war, environmental collapse, or artificial intelligence gone awry. If this pattern holds true, it could mean that long-lived peaceful civilizations are exceedingly scarce. Some speculate that aliens might be deliberately avoiding us, either because they see no benefit in contacting us or because they wish to observe us without interference, a concept known as the zoo hypothesis. Alternatively, they might communicate in ways we can't detect using technologies far beyond our understanding. Perhaps the problem lies not with the universe, but with us. Our methods of searching for extraterrestrial life are limited by our technology and imagination. We look for radio signals, chemical signatures, and patterns familiar to us. But what if alien civilizations operate on entirely different principles? For instance, imagine trying to detect a civilization that communicates through quantum entanglement or manipulates dark matter. Their presence might be invisible to us, like trying to hear a symphony while being deaf to its frequencies. The Fermi Paradox reminds us how much we still don't know about the cosmos and ourselves. The Fermi Paradox challenges us to confront fundamental questions about life, intelligence, and our place in the universe. Is humanity unique, or are we part of a cosmic community waiting to be discovered? Does the absence of evidence imply evidence of absence, or simply highlight the vastness of space and time? As you gaze up at the night sky, let yourself wonder about the possibilities. Somewhere out there, perhaps another civilization is asking the same question: where is everyone? The Fermi Paradox is a reminder of both the beauty and the mystery of the universe. Whether we're alone or surrounded by unseen neighbors, the search for answers connects us to something greater than ourselves. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far beyond our comprehension. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the universe as we know it is just a sliver of reality? What if beyond the 3 dimensions we experience every day, length, width, and height, there exist hidden dimensions, unseen and unfathomable to our senses? Our everyday experience tells us that the universe has 3 spatial dimensions and 1 dimension of time. But what if this is only part of the story? Scientists have long speculated that there might be additional dimensions beyond those we can perceive, dimensions that could hold the key to understanding some of the deepest mysteries of the cosmos. These hidden dimensions are not just the stuff of science fiction. They arise naturally in advanced theories like string theory, which attempts to unify all the forces of nature into a single framework. According to string theory, the fundamental building blocks of the universe are not particles, but tiny vibrating strings. And for these strings to behave the way they do, the universe must have more than the familiar 4 dimensions, possibly as many as 10 or 11. So, what would these extra dimensions look like? Unlike the ones we're used to, they might be compactified, curled up so tightly that they're invisible to us at everyday scales. Imagine a garden hose viewed from far away. It appears one-dimensional, like a straight line. But up close, you can see that it has a second dimension, a circular cross-section. Similarly, extra dimensions might be curled up into shapes so small that we don't notice them in our daily lives. Some physicists suggest these dimensions could take the form of intricate geometries, such as Calabi-Yau manifolds, complex multidimensional shapes that influence how particles and forces behave. These dimensions might also explain why gravity is so much weaker than the other fundamental forces. It could be leaking into these hidden realms. If extra dimensions exist, why can't we detect them? One possibility is that they're simply too small for our current technology to measure. Another idea is that we're confined to a brain, a 3-dimensional slice of a higher dimensional space. Think of it like living on the surface of a vast ocean. You can move freely across its expanse, but you can't step off into the air above or dive into the depths below without special tools. This concept raises fascinating questions about the nature of reality. Could beings in these extra dimensions perceive the universe in ways we can't imagine? Might they see time as another spatial direction or view our entire history laid out before them like a map? The existence of extra dimensions could help solve some of the biggest puzzles in physics. For instance, they might explain why the constants of nature, like the strength of gravity or the speed of light, have the values they do. They could also shed light on dark matter and dark energy, which make up most of the universe but remain mysterious to us. Imagine standing at the edge of a multidimensional universe, peering into realms beyond human comprehension. These dimensions might connect distant parts of the cosmos through wormholes or allow for parallel universes where alternate versions of ourselves live out different lives. The possibilities are as endless as they are mind-bending. The idea of hidden dimensions reminds us that reality is far stranger and more complex than we often assume. Whether they're curled up invisibly within the fabric of space-time or stretching infinitely beyond our reach, these dimensions challenge us to expand our understanding of the universe and ourselves. Let this thought lull you deeper but into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the universe is not just expanding, but speeding up as it grows? What invisible force could be driving this acceleration, stretching the cosmos farther and faster with each passing moment? Our journey begins with a shocking discovery made in the late 1990s. Scientists studying distant supernovae, exploding stars, found something unexpected. Instead of slowing down due to gravity, the expansion of the universe was actually accelerating. Something out there was counteracting the pull of gravity, pushing galaxies apart at an ever-increasing rate. This unseen force was dubbed dark energy, a placeholder name for a phenomenon we still don't fully understand. Despite making up roughly 1/6 of the universe, dark energy leaves no direct trace. It doesn't emit light, interact with matter, or reveal itself through conventional means. Yet its effects are undeniable, shaping the very fabric of space-time itself. So, how do we know dark energy is real? Beyond the observations of supernovae, other lines of evidence point to its existence. For instance, measurements of the cosmic microwave background, the afterglow of the Big Bang, show that ordinary matter and dark matter alone can't account for the total energy density of the universe. Something else must be filling the gap. Additionally, astronomers have mapped the distribution of galaxies across vast regions of space. These maps reveal patterns consistent with the universe being stretched thin by an accelerating force. Together, these clues paint a picture of a cosmos dominated by dark energy, quietly steering its ultimate fate. But what exactly is dark energy? One leading theory suggests it's a property of space itself, often referred to as the cosmological constant. In this view, Empty space isn't truly empty. It contains intrinsic energy that causes it to expand. As the universe grows, so does the amount of space, amplifying the effect of dark energy over time. Another possibility is that dark energy is a dynamic field, sometimes called quintessence, that changes strength over time. Unlike the cosmological constant, quintessence could vary across different regions of the universe, offering a more complex explanation for its behavior. Some physicists even propose radical ideas that our understanding of gravity might be incomplete, or that dark energy is linked to higher dimensions beyond our perception. At this point, all options remain on the table. The mystery of dark energy isn't just an academic question. It holds the key to understanding the future of the universe. If dark energy continues to dominate, the cosmos will expand indefinitely, leading to a cold, lonely end known as the heat death. Galaxies will drift apart, stars will burn out, and the universe will become a dark, desolate expanse. On the other hand, if dark energy behaves unpredictably, if it weakens or reverses, the universe could collapse inward in a fiery big crunch or tear itself apart in a catastrophic big rip. Each scenario hinges on the true nature of this elusive force. Dark energy reminds us that the universe is far stranger than we can imagine. It challenges our understanding of physics, forces us to confront the limits of human knowledge, and invites us to dream of possibilities beyond our grasp. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if there's a mark on the map of the universe, a mysterious cold spot in the ancient light of creation that hints at something beyond our cosmos? Could it be evidence of another universe brushing against our own? In 2004, scientists analyzing data from the Wilkinson Microwave Anisotropy Probe, WMAP, discovered something strange, a vast region in the cosmic microwave background, CM, the afterglow of the Big Bang, that was unusually cold and empty. This area, known as the cold spot, spans about 1.8 billion light-years across, making it one of the largest structures ever observed. At first glance, the cold spot seems out of place, while the rest of the CMB shows tiny fluctuations in temperature, tiny ripples that eventually led to the formation of galaxies and stars. The cold spot is an enormous void, colder and emptier than expected. But why does it exist? And what could it mean for our understanding of the universe? One explanation is that the cold spot is simply a massive supervoid, a region of space with far fewer galaxies than average. In this scenario, photons from the CMB lose energy as they pass through this void due to the lack of gravitational pull, creating the appearance of a colder spot. However, studies have struggled to confirm the existence of such a vast void, leaving this theory unresolved. Another more speculative idea suggests that the cold spot could be evidence of a collision between our universe and another one. According to some versions of the multiverse theory, our universe isn't alone. It may exist alongside countless others, occasionally interacting in ways we're only beginning to understand. A collision with another universe could leave behind scars like ripples in the fabric of space-time, visible in the CMB as anomalies like the cold spot. The concept of the multiverse challenges our understanding of reality. Imagine a kaleidoscope of universes, each with its own laws of physics, constants, and dimensions. Some might be eerily similar to ours, while others could be unimaginably different. If true, these parallel universes might occasionally collide or interact, leaving traces in our observable universe. The cold spot could be one such trace, a fingerprint of another universe brushing against ours during the earliest moments of time. While this idea remains highly speculative, it has captured the imagination of scientists and philosophers alike, offering a tantalizing glimpse into what might lie beyond the boundaries of our observable reality. But how can we test such an extraordinary claim? Detecting evidence of another universe is no small feat. Scientists are looking for patterns in the CM that might support the multiverse hypothesis, such as specific signatures of cosmic collisions. Advanced telescopes and observational techniques like those used by the Planck satellite are helping researchers study the CMB in unprecedented detail. Even so, proving the existence of another universe is extraordinarily difficult. For now, the cold spot remains an enigma, a puzzle waiting to be solved. Whether it's a supervoid, a glitch in our models, or evidence of a multiverse, its presence reminds us that the universe is full of surprises. The cold spot invites us to dream of possibilities beyond the edges of our known universe. It challenges us to imagine realities far stranger and more complex than anything we've encountered before. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if there were shortcuts through the universe? Hidden passages that could take you from one corner of the cosmos to another in the blink of an eye. What if wormholes, those fantastical bridges through space-time, weren't just science fiction, but a real possibility? Wormholes are hypothetical structures predicted by Einstein's theory of general relativity. Imagine them as tunnels connecting two distant points in space-time, like a secret doorway between galaxies, stars, or even parallel universes. If they exist, they could allow for faster-than-light travel, or at least the illusion of it, by creating shortcuts across the vastness of space. But here's the catch. While the mathematics of general relativity allows for their existence, no one has ever observed a wormhole. And even if they do exist, the challenges involved in finding or using them are immense. To understand wormholes, picture space-time as a flexible fabric. According to Einstein's equations, massive objects like black holes warp this fabric, bending light and time around them. A wormhole takes this idea further. It's like folding the fabric so that two distant points touch, creating a tunnel between them. These tunnels, often referred to as Einstein-Rosen bridges, were first proposed in the 1930s by Albert Einstein and Nathan Rosen. However, these early models suggested that such bridges would collapse almost instantly, making them useless for travel unless something extraordinary held them open. One of the biggest hurdles is stability. As far as we know, wormholes would require a form of exotic matter with negative energy to keep them from collapsing. This hypothetical material would have properties unlike anything we've observed in nature. It would repel gravity instead of attracting it, effectively acting as a counterforce to hold the wormhole open. While exotic matter remains purely speculative, some physicists suggest that quantum mechanics might provide clues. For instance, phenomena like the Casimir effect demonstrate how empty space can exhibit negative energy under certain conditions. Could this be a hint that the ingredients for stable wormholes exist somewhere in the universe? If wormholes exist, they might occur naturally, born from the extreme conditions of the early universe. Some theories propose that tiny wormholes could have formed during the Big Bang, lingering as microscopic remnants scattered throughout space-time. These primordial wormholes would be far too small for humans to traverse. But with advanced technology, could we enlarge them? Alternatively, wormholes might be artificial constructs, engineered by civilizations far more advanced than ours. Imagine beings capable of manipulating space-time itself, building cosmic highways to explore the universe. If such civilizations exist, their wormholes could be hidden in plain sight, waiting for us to discover them. Traveling through a wormhole would be unlike anything we've experienced. You'd enter one end, perhaps near Earth, and emerge from the other end in a distant galaxy, or even a different time. The journey inside might feel surreal, with warped light and distorted shapes stretching and swirling around you. But beware, wormholes could also be dangerous. They might contain intense gravitational forces, radiation, or unpredictable fluctuations. One wrong step and you could find yourself crushed, stretched into oblivion, or worse, trapped forever in an unstable tunnel. The idea of wormholes reminds us of the boundless possibilities of the universe. Whether they're natural wonders or feats of alien engineering, they challenge us to dream beyond the limits of our current understanding. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the universe was born with equal parts matter and antimatter, perfect opposites, destined to annihilate each other completely? If that's true, why does matter dominate the cosmos today? Why are we here at all? To understand the mystery, we must go back to the very beginning, the Big Bang. According to our best theories, the early universe should have produced equal amounts of matter and antimatter. These two forms of substance are mirror images of each other, identical in every way except for their opposite charges. When matter meets antimatter, they annihilate in a burst of energy, leaving nothing behind. So, Here's the paradox. If matter and antimatter were created in equal quantities, they should have destroyed each other entirely. Yet here we are, a universe filled with galaxies, stellar planets, and life, all made of matter. Where did all the antimatter go? The answer lies in something called CP violation, a subtle asymmetry in the laws of physics that might explain why matter survived while antimatter didn't. CP stands for charge parity, and it refers to how particles behave under certain transformations. In a perfectly symmetrical universe, matter and antimatter would behave identically, leading to mutual destruction. But experiments have shown that some particles don't follow this symmetry as strictly as expected. For example, quarks, the building blocks of protons and neutrons, exhibit slight differences in behavior compared to their antimatter counterparts. These tiny discrepancies may have allowed a small fraction of matter to survive the primordial annihilation. However, the amount of surviving matter predicted by current models is still far too small to account for the vast amounts we see today. One promising area of research focuses on neutrinos, those ghostly subatomic particles that rarely interact with anything. Scientists suspect that neutrinos might also violate CP symmetry in ways we don't fully understand yet. If confirmed, this could help explain why matter gained the upper hand in the cosmic battle against antimatter. Imagine a universe where neutrinos tip the scales ever so slightly, allowing matter to win out. It's a humbling thought, one that reminds us how delicate and improbable our existence truly is. Experiments around the world are working tirelessly to solve this riddle. Particle accelerators like CERN's Large Hadron Collider smash particles together at near light speeds, recreating conditions similar to those just after the Big Bang. Researchers hope to uncover new clues about CP violation and the fundamental forces shaping the universe. At the same time, telescopes scour the cosmos for signs of antimatter regions. So far, no significant pockets of antimatter have been found. This suggests that whatever process favored matter happened universally, or nearly so. The missing antimatter problem isn't just an academic question. It strikes at the heart of why we exist. If the balance had shifted even slightly toward antimatter, there would be no stars, no planets, and no life as we know it. Instead, the universe would be a desolate expanse of radiation left over from countless annihilations. This mystery challenges us to rethink our assumptions about the fundamental nature of reality. It forces us to confront the possibility that the universe is not as symmetrical or predictable as we once believed. The dominance of matter over antimatter is a reminder of how fragile and extraordinary our existence is. A tiny imbalance, an almost imperceptible tilt in the scales of creation, has given rise to everything we see, touch, and experience. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the universe is whispering to us through an eerie hum, a constant, unexplained radio signal emanating from the depths of space. What could be creating this mysterious noise, and what does it mean for our understanding of the cosmos? In recent years, astronomers have detected something truly baffling, a persistent, low-frequency hum permeating the universe. This isn't the kind of signal you'd expect from stars, galaxies, or any known celestial object. Instead, it's a diffuse background buzz that seems to come from everywhere and nowhere at once. This hum has been picked up by highly sensitive radio telescopes designed to listen to the faintest whispers of the cosmos. It exists in the form of the long wavelength radio waves, far below the frequencies typically associated with natural astrophysical processes like pulsars or black holes. So where does it come from? One possibility is that this hum originates from the earliest moments of the universe. Just as the cosmic microwave background preserves a snapshot of the Big Bang, these radio signals might carry echoes of events that occurred shortly after the universe was born. Perhaps they're remnants of primordial magnetic fields or acidic particles that shaped the infant cosmos. Another theory suggests that the hum could be linked to dark matter, the invisible substance making up most of the universe. Some models predict that dark matter particles might occasionally annihilate or decay, releasing energy in the form of radio waves. If true, this would provide a groundbreaking way to study one of the greatest mysteries of modern physics. Of course, there's always the tantalizing possibility that this hum is evidence of something entirely new, something humanity has never encountered before. Could it be a sign of advanced alien civilizations communicating across vast distances? Or perhaps it's a clue pointing to physics beyond our current understanding, revealing forces or dimensions hidden from view. Some researchers speculate that the hum might even originate from outside our observable universe. Imagine a multiverse filled with countless other realities, each leaving subtle imprints on the fabric of space-time. Could this hum be a fingerprint of those alternate realms, brushing against our own? But here's the catch. Detecting and interpreting this hum is incredibly difficult. The signals are incredibly faint, buried beneath layers of noise from Earth-based interference, solar activity, and other cosmic sources. Scientists must sift through mountains of data to isolate the hum, often relying on advanced algorithms and machine learning techniques. Even when they succeed, the results raise more questions than answers. Why does the hum appear so uniform across the sky? How can we pinpoint its exact origin? And most importantly, what does it tell us about the fundamental nature of reality? The eerie hum of deep space radio signals reminds us how much we still don't know about the universe. It challenges our assumptions about what lies beyond the stars and encourages us to keep searching for answers, no matter how elusive they may seem. Just imagine lying under the night sky, knowing that somewhere out there, an unseen force is broadcasting a message we're only beginning to hear. Whether it's a relic of the Big Bang, a sign of dark matter, or something stranger still, the hum invites us to dream of possibilities beyond our grasp. The eerie hum of deep space is a reminder that the universe is full of secrets waiting to be uncovered. Its presence stirs both awe and curiosity, reminding us that the quest for knowledge is endless. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if there were worlds out there unlike anything we've ever imagined? Planets so rich in carbon that their very cores could be made of diamond. Could such glittering treasures exist beyond our solar system? Our journey begins with an intriguing possibility raised by astronomers studying exoplanets, planets orbiting stars other than our sun. Some of these distant worlds may form in environments vastly different from Earth's, where carbon is far more abundant than oxygen. In such systems, planets might not have silicate-rich crusts like ours, but instead could consist largely of graphite and diamond. Imagine a planet with mountains of pure diamond, sparkling under alien skies, a cosmic jewel floating in the void of space. To understand how diamond planets might come to exist, we must first look at the chemistry of star systems. In our own solar system, oxygen dominates over carbon, leading to rocky planets like Earth, composed mostly of silicates. But in star systems, where carbon outweighs oxygen, conditions are ripe for extraordinary planetary compositions. One theory suggests that these carbon-rich planets form around stars with high levels of carbon. As material coalesces into planets, intense pressure deep within their interiors could transform carbon into diamond on a massive scale. These planets wouldn't just have pockets of precious gems. They might literally be built from them. One of the most famous candidates for a diamond planet is 55 Cancri, located about 40 light-years away in the constellation Cancer. This super-Earth orbits its host star so closely that its surface temperature exceeds 2,000 degrees Celsius, hot enough to melt rock. Early studies hinted that 55 Cancri might contain a significant amount of carbon, potentially forming a layer of diamond beneath its surface. While later research has cast doubt on this idea, suggesting it may be more water-rich than previously thought, the possibility remains tantalizing. Somewhere out there, a true diamond planet might still await discovery. Detecting diamond planets presents unique challenges. Unlike gas giants or rocky planets, which reveal themselves through observable properties like mass, size, and atmospheric composition, diamond planets require us to infer their makeup indirectly. Scientists analyze the chemical signatures of host stars to predict what kinds of planets might form around them. If a star has a high carbon-to-oxygen ratio, its planets are more likely to be carbon-rich. However, confirming whether those planets actually contain diamonds requires advanced telescopes and techniques that can peer into their depths, a task far beyond current technology. Imagine standing on the surface of a diamond planet. The landscape might shimmer with crystalline structures, reflecting light in dazzling ways. Beneath your feet could lie layers upon layers of compressed carbon forged over billions of years under unimaginable pressure. But don't expect to mine these treasures anytime soon. Even if humans could reach such a world, the extreme temperatures and pressures would make exploration nearly impossible. Still, the mere existence of such a planet would challenge everything we know about planetary formation and the diversity of worlds in the cosmos. The search for diamond planets isn't just about finding cosmic riches. It's about understanding the incredible variety of worlds that exist beyond our solar system. Each new discovery teaches us something profound about the forces that shape the universe and the endless possibilities of creation. These planets remind us that the cosmos is full of surprises, defying our expectations and inspiring us to dream of futures we can scarcely imagine. The idea of diamond planets invites us to marvel at the wonders of the universe. Whether they're real or remain a tantalizing hypothesis, they spark our curiosity and remind us of the infinite creativity of nature. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if there are planets out there, untethered to any star, wandering endlessly through the cold vastness of space? These rogue planets, adrift in the darkness, may number in the billions, hidden worlds with secrets all their own. Rogue planets, also known as free-floating or orphan planets, are celestial bodies that do not orbit a star. Instead, they drift alone through interstellar space, far from the warmth and light of a sun. Some were likely ejected from their home systems during chaotic gravitational interactions, while others may have formed independently in the depths of space, much like stars. These lonely wanderers challenge our traditional understanding of what makes a planet. Without a star to call home, they exist in perpetual darkness, their surfaces frozen and barren, or so we assume. But could some rogue planets harbor hidden surprises beneath their icy exteriors? There are two main theories about how rogue planets come to be. The first suggests they were once part of planetary systems, but were flung out due to violent gravitational encounters. Imagine a young solar system, still chaotic and unstable, where massive gas giants jostle for position. In such a turbulent environment, smaller planets can be hurled into the void, destined to roam the galaxy forever. The second theory posits that rogue planets form directly from collapsing clouds of gas and dust, similar to how stars are born. However, these objects lack the mass needed to ignite nuclear fusion, leaving them as dark, cold remnants of stellar nurseries. These failed stars blur the line between planets and brown dwarfs, adding another layer of intrigue to their nature. Finding rogue planets is no easy task. Without a host star to illuminate them, these shadowy worlds are nearly impossible to detect using conventional methods. Most have been discovered through a technique called gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity acts like a lens, briefly magnifying the star's light. This fleeting glow reveals the presence of the otherwise invisible wanderer. Scientists estimate that rogue planets may outnumber stars in the Milky Way, meaning there could be billions or even trillions of these drifting worlds scattered throughout our galaxy. Yet, we've only scratched the surface of identifying them. One of the most fascinating questions about rogue planets is whether they could support life. On the surface, it seems unlikely. Without a nearby star, temperatures plummet to unimaginable lows. But beneath thick layers of ice, heated by internal processes like radioactive decay or residual formation energy, liquid water oceans might exist. Consider Europa, one of Jupiter's moons, which harbors a subsurface ocean despite being far from the sun. If rogue planets have similar conditions, they could theoretically provide a haven for microbial life, or even more complex organisms shielded from the harshness of space. Imagine approaching a rogue planet. There would be no glowing orb in the sky, no sunrise or sunset, just an endless expanse of blackness stretching in every direction. The planet itself might be shrouded in frost, its surface sculpted by aeons of exposure to the frigid interstellar medium. If you ventured closer, advanced instruments might reveal strange landscapes carved by ancient volcanic activity or geysers spewing plumes of vapor into the void. And deep below, who knows? Perhaps hydrothermal vents teeming with alien chemosynthetic ecosystems await discovery. The existence of rogue planets reminds us of the diversity and resilience of the universe. They challenge our assumptions about where life might arise and what defines a habitable world. Each rogue planet is a testament to the dynamic forces that shape the cosmos, from the chaos of newborn systems to the quiet solitude of interstellar space. These wandering worlds also raise profound philosophical questions. Are we alone in the universe? Could rogue planets serve as stepping stones for future interstellar exploration? Their presence invites us to dream of possibilities beyond the familiar boundaries of our solar system. Rogue planets remind us that even in the darkest corners of the universe, wonders abound. Whether they're relics of shattered systems or solitary wanderers forged in isolation, they embody the mystery and beauty of the cosmos. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine and the universe feels just a little more infinite. What lies beyond the farthest reaches of the cosmos? Is there an edge to the universe? A boundary where everything we know simply stops? Or does the universe stretch infinitely, defying our ability to comprehend its vastness? When we talk about the edge of the universe, we're not referring to a literal wall or cliff. Instead, we're asking about the limits of what exists, the outermost regions of space and time that define our observable reality. Our current understanding suggests that the universe has no physical edge in the traditional sense. Instead, it's expanding outward, with galaxies moving farther apart as space-time itself stretches. But this raises another question. If the universe is infinite, how can it still be expanding? And if it's finite, what lies beyond? The part of the universe we can see, the observable universe, is roughly 93 billion light years across. This horizon exists because light from objects beyond this range hasn't had enough time to reach us since the Big Bang 13.8 billion years ago. But here's the twist. The observable universe is just a tiny fraction of the entire cosmos. Beyond this horizon, there could be infinitely more stars, galaxies, and mysteries waiting to be discovered, or something entirely different altogether. If you were somehow able to travel to the very limit of the observable universe, you wouldn't find a sudden stop or a brick wall. Instead, you'd encounter a region where space-time continues to expand faster than the speed of light due to dark energy. Any light emitted from beyond this point would never reach you. It would literally recede out of sight as quickly as you approached it. This concept challenges our intuition. The universe isn't confined within walls. It's a dynamic, ever-growing expanse. Yet, the idea of infinity remains difficult to grasp. How can something have no end, yet constantly grow larger? One possibility is that the universe is truly infinite, a boundless ocean of matter, energy, and empty space, stretching endlessly in every direction. In this scenario, there is no edge, only an unending continuum of existence. On the other hand, some theories propose that the universe might be finite but without boundaries. Imagine the surface of a sphere. It's finite, but you can walk forever around it without encountering an edge. Similarly, the fabric of space-time could curve back on itself in 4 dimensions, creating a closed loop where traveling far enough in one direction eventually brings you back to your starting point. Some physicists speculate that our universe may not be unique. According to multiverse theories, our cosmos could be just one bubble in a vast sea of universes, each with its own laws of physics, constants, and properties. If true, the edge of our universe might mark the transition into these neighboring realms. Imagine stepping through such a boundary, not into emptiness, but into a completely alien reality. These ideas push the limits of human imagination, reminding us that the universe is far stranger and more complex than we often assume. The question of what lies at the edge of the universe isn't just academic. It speaks to our deepest yearnings for meaning and understanding. Are we alone in an infinite cosmos, or do other worlds and civilizations exist beyond our perception? These musings invite us to embrace the unknown, finding peace in the vastness of what we cannot yet comprehend. Whether the universe is infinite or bounded, its mysteries connect us to something greater than ourselves. The edge of the universe reminds us that curiosity is one of humanity's greatest gifts. Even if we never find definitive answers, the act of seeking them expands our horizons and deepens our appreciation for the cosmos. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the universe is sending us brief, powerful messages? Flashes of energy so intense they outshine entire galaxies for just a fraction of a second. These are fast radio bursts, mysterious signals that pulse through the cosmos and vanish almost as quickly as they appear. Fast radio bursts, or FRBs, are some of the most perplexing phenomena ever detected in the universe. These millisecond-long bursts of radio waves release an immense amount of energy, equivalent to what our sun emits over decades, in less than the blink of an eye. First discovered in 2007, they have left scientists scrambling to understand their origins. Imagine standing under a night sky, knowing that somewhere out there, a distant source is releasing these fleeting flashes of energy. But where do they come from, and why are they so short-lived? FRBs are bursts of electromagnetic radiation that last only a few milliseconds but pack an incredible punch. They originate from far beyond our galaxy, often traveling billions of light years before reaching Earth. Despite their brevity, these signals carry clues about the vast distances they traverse, including information about the matter and magnetic fields between galaxies. Some FRBs repeat, flashing multiple times from the same location, while others appear as one-time events. This diversity has deepened the mystery, suggesting that different mechanisms, or even multiple sources, could be responsible. One leading theory suggests that FRBs could be caused by highly magnetized neutron stars called magnetars. These stellar remnants possess incredibly strong magnetic fields capable of producing energetic outbursts. In fact, astronomers recently detected an FRB originating from within our own Milky Way, traced back to a magnetar, a breakthrough discovery that supports this idea. However, not all FRBs fit neatly into this explanation. Some researchers propose more exotic possibilities, such as collisions between compact objects like black holes or neutron stars, or even advanced alien technologies attempting to communicate across the cosmos. While the latter remains speculative, it underscores how little we truly know about these enigmatic signals. The transient nature of FRB makes them notoriously difficult to study. By the time telescopes detect a burst, it's already gone. To catch these elusive signals, astronomers rely on cutting-edge instruments like the CHIME, Canadian Hydrogen Intensity Mapping Experiment, telescope, which can monitor large portions of the sky continuously. Even when detected, pinpointing their exact locations requires rapid coordination among observatories worldwide. Each new detection brings us closer to unraveling the mystery, but many questions remain unanswered. Beyond their mysterious origins, FRBs offer a unique window into the universe. As these signals travel across billions of light years, they interact with intergalactic material, providing insights into the composition and structure of the cosmos. Scientists use FRBs to map the distribution of matter between galaxies, shedding light on the cosmic web that connects everything in the universe. They also challenge our understanding of extreme astrophysical environments. Whether born from catastrophic explosions or exotic objects, FRBs push the boundaries of what we think is possible in the universe. Fast radio bursts remind us that the universe is full of surprises, flashing its secrets across unimaginable distances in the blink of an eye. Their fleeting nature invites us to stay curious, to keep searching for answers in the vast unknown. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if our universe isn't the only one? What if, beyond the edges of what we can see, countless other realities exist? Parallel universes where different versions of you live out alternate lives. The concept of parallel universes arises from theories that challenge our understanding of reality. Imagine a multiverse, a vast collection of universes, each with its own laws of physics, history, and possibilities. In some, dinosaurs never went extinct. In others, humanity may have colonized the stars or never existed at all. While the idea sounds like science fiction, it's rooted in serious scientific inquiry. From quantum mechanics to cosmology, several frameworks suggest that our universe might not be unique. But how could such a thing be possible? One of the most famous arguments for parallel universes comes from quantum mechanics, the branch of physics that describes the behavior of particles at the smallest scales. According to the many worlds interpretation, every decision or event creates a branching of realities. For example, imagine flipping a coin. In one universe, it lands heads, in another, tails. These branches multiply endlessly, creating an infinite number of parallel worlds, each representing a different outcome. While we experience only one path, the other possibilities continue to unfold unseen. Another theory involves cosmic inflation, the rapid expansion of space that occurred just after the Big Bang. Some physicists propose that this process didn't stop everywhere. Instead, regions of space kept inflating, forming bubble universes within a larger multiverse. Each bubble would have its own physical constants and properties. For instance, gravity might work differently, or light might not exist at all. Our universe is simply one bubble among many, floating in an endless sea of potential realities. String theory offers yet another perspective on parallel universes. This framework suggests that the fundamental building blocks of the universe are tiny, vibrating strings. Depending on how these strings vibrate, they give rise to different particles and forces. In string theory, there could be as many as 500 possible configurations of the universe, each corresponding to a unique set of physical laws. This landscape of universes raises the possibility that our cosmos is just one solution in a grander multiverse equation. One of the biggest challenges is detecting evidence of parallel universes. By definition, they lie beyond the observable universe, making direct observation impossible. However, scientists are searching for indirect clues. For instance, some researchers speculate that collisions between our universe and neighboring ones might leave imprints on the cosmic microwave background. A faint glow left over from the Big Bang, Others look for anomalies in particle physics that could hint at interactions with other dimensions or universes. The question of parallel universes isn't just academic. It touches on profound philosophical issues. If multiple realities exist, what does it mean for free will, identity, and the uniqueness of our experiences? Imagine lying under the stars, knowing that somewhere out there, another version of you might be gazing at a completely different sky. Whether true or not, the idea invites us to embrace the infinite possibilities of existence. The notion of parallel universes reminds us that reality is far stranger and more complex than we often assume. Whether they're real or remain a tantalizing hypothesis, they spark our curiosity and inspire us to dream of futures we can scarcely imagine. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What happens when two of the most powerful and mysterious objects in the universe collide? Imagine two black holes spiraling toward each other, their immense gravitational forces warping space-time itself. The result is one of the most cataclysmic events in the cosmos, a black hole merger. When two black holes come close enough, they begin an intricate dance governed by gravity. As they orbit each other, they emit gravitational waves, ripples in space-time that stretch and squeeze the fabric of the universe. These waves carry away energy, causing the black holes to spiral closer and faster until they finally merge into a single, more massive black hole. This process is not just theoretical. Astronomers have detected these mergers using instruments like LIGO, Laser Interferometer, Gravitational Wave Observatory, and Virgo. Each detection provides a glimpse into the violent yet beautiful dynamics of the cosmos. As the black holes approach each other, their orbital speeds reach incredible velocities, up to half the speed of light. At this point, the gravitational waves become so intense that they can be detected billions of light years away. When the event horizons of the two black holes touch, they coalesce into a single entity, sending out a final, powerful burst of gravitational radiation. For a brief moment, the newly formed black hole isn't perfectly spherical. It wobbles and vibrates, a phase known as ring down, as it settles into a stable configuration. This ringing produces its own unique signature of gravitational waves, offering scientists clues about the properties of the merged black hole. The resulting black hole is typically more massive than the sum of the original two, but not entirely. Some of the mass is converted into energy during the merger, released primarily in the form of gravitational waves. In fact, these collisions release more energy in a fraction of a second than all the stars in the observable universe combined. The new black hole may also receive a kick from the asymmetric emission of gravitational waves, propelling it through space at high speeds. Such rogue black holes could wander galaxies, leaving behind trails of disrupted stars and gas. Black hole mergers are more than just spectacular displays of cosmic power. They're laboratories for testing our understanding of physics They help confirm predictions made by Einstein's theory of general relativity and provide insights into the nature of space-time, gravity, and the life cycle of black holes. These events also shed light on how supermassive black holes grow over time. By merging with smaller black holes or stellar mass companions, they accumulate mass and influence the evolution of galaxies. If you were unlucky enough to find yourself near two merging black holes, survival would be impossible. The tidal forces, differences in gravity across your body, would stretch you into a long, thin strand in a process aptly named spaghettification. Even spacecraft equipped with advanced technology wouldn't stand a chance against such extreme conditions. However, observing these mergers from afar allows us to safely marvel at their grandeur. Through gravitational wave astronomy, we've opened a new window into the universe, hearing the sounds of these colossal collisions echo across the cosmos. The merger of two black holes is a reminder of the raw power and elegance of the universe. It challenges us to think beyond our everyday experiences and embrace the mysteries that lie at the edges of human knowledge. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if you could step into a machine, press a button, and find yourself in the distant past or far-off future? Could time travel ever be more than just science fiction? A tangible reality we could one day experience? Time travel has captivated our imaginations for centuries, from ancient myths to modern blockbusters. But is it truly within the realm of possibility? To answer that, we must first turn to physics, the rules that govern the universe, and see where they leave room for bending time. One of the most intriguing frameworks comes from Albert Einstein's theory of relativity. According to this groundbreaking work, time isn't fixed. It flows differently depending on speed and gravity. This means time can stretch or contract under certain conditions, creating opportunities that seem almost like traveling through time. Einstein's theory predicts phenomena like time dilation, which occurs when an object moves at speeds close to the speed of light. For example, astronauts orbiting Earth age slightly slower than those of us on the ground due to their high velocity. While this effect is minuscule at human scale speeds, it becomes dramatic near light speed. In theory, someone traveling close to the speed of light could return to Earth decades or even centuries later, while only experiencing a few years themselves. Another possibility lies in the extreme gravitational pull of black holes. Near the event horizon, the boundary beyond which nothing escapes, a phenomenon called gravitational time dilation occurs. Time slows down significantly for anyone near a black hole compared to observers farther away. Imagine spending a short time orbiting a black hole and returning to find centuries have passed on Earth. But time travel isn't without its paradoxes, logical contradictions that challenge its feasibility. Take the famous grandfather paradox. What happens if you go back in time and accidentally prevent your grandparents from meeting? If you were never born, how could you have traveled back in time to cause the disruption? Such paradoxes suggest that backward time travel might create inconsistencies that break the fabric of reality. Some physicists propose solutions to these paradoxes, such as the idea of branching timelines. In this multiverse-inspired model, changing the past creates a new alternate timeline rather than altering the original one. Others argue that backward time travel may simply be impossible, leaving us free to explore only forward journeys into the future. If time travel is theoretically possible, could we build a machine to achieve it? Concepts like wormholes, hypothetical tunnels, connecting distant points in space-time offer tantalizing possibilities. A stable wormhole could act as a portal, allowing travelers to leap across vast stretches of time and space. However, keeping such a structure open would require exotic matter with negative energy, something we've yet to discover or create. Another speculative idea involves manipulating massive amounts of energy to warp space-time itself. Theoretical physicist Kip Thorne once proposed using rotating cylinders of neutron star material to twist time into loops, enabling closed time-like curves, paths that circle back to earlier moments. But constructing such devices remains firmly in the realm of speculation. Even if time travel becomes possible, profound ethical questions arise. Would changing the past improve our world or unleash chaos? And what responsibilities would come with knowing the future? These dilemmas force us to confront not just the science of time travel, but also its impact on morality and free will. Imagine standing at the threshold of a time machine, faced with the choice to visit any era. Would you seek wisdom from history's greatest minds, witness pivotal moments firsthand, or glimpse humanity's destiny among the stars? Or would you hesitate, knowing the risks involved? The dream of time travel reminds us of our innate desire to transcend limitations, to explore the uncharted territories of both the past and the future. Whether it remains a fantasy or someday becomes a reality, the pursuit itself deepens our connection to the mysteries of existence. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the colossal supermassive black holes at the centers of galaxies aren't just gravitational monsters, but gateways to other parts of the universe, or even other universes altogether? Could these enigmatic giants be hiding wormholes, waiting to reveal their secrets? Supermassive black holes are among the most powerful and mysterious objects in the universe. These behemoths, with masses millions or even billions of times that of our Sun, reside at the hearts of nearly every galaxy, including our own Milky Way. Their immense gravity warps space-time so severely that not even light can escape their grasp. But what if these cosmic titans are more than just destructive forces? Some physicists speculate that supermassive black holes could harbor wormholes, hypothetical tunnels through space-time that might connect distant regions of the universe or even entirely separate realities. Wormholes, also known as Einstein-Rosen bridges, are theoretical structures predicted by Einstein's theory of general relativity. Imagine folding a piece of paper so that two distant points touch. A wormhole would act as a shortcut between those points, bypassing the vast distances in between. While no direct evidence for wormholes exists, their possibility has intrigued scientists and science fiction enthusiasts alike. If they do exist, they could revolutionize our understanding of the cosmos, offering potential pathways for interstellar travel or even communication across unimaginable distances. One intriguing idea is that supermassive black holes might serve as natural candidates for wormhole entrances. Unlike stellar mass black holes, which form from collapsing stars, supermassive black holes have origins that remain poorly understood. Some theories suggest they could have formed directly from primordial conditions in the early universe, making them ideal candidates for harboring exotic structures like wormholes. Imagine approaching the event horizon of a supermassive black hole. Instead of being crushed into oblivion, you might instead find yourself entering a tunnel, a passage leading to another part of the universe or an entirely different cosmos. Detecting a wormhole hidden within a supermassive black hole presents significant challenges. The extreme gravitational forces and intense radiation surrounding these objects make detailed observations nearly impossible with current technology. However, scientists propose several ways we might identify such a phenomenon. For instance, if a wormhole were present, it could produce unique gravitational lensing effects, distortions in the light from background stars and galaxies caused by the curvature of space-time. Additionally, matter falling into a wormhole might behave differently than it would in a typical black hole, potentially emitting distinctive signatures detectable by telescopes. One of the biggest hurdles in the existence of wormholes is stability. As far as we know, wormholes would require a form of exotic matter with negative energy to keep them open against the crushing force of gravity. This hypothetical material would repel gravity instead of attracting it, effectively acting as a counterforce to prevent collapse. While exotic matter remains purely speculative, some researchers suggest that quantum mechanics might provide clues. Phenomena like the Casimir effect demonstrate how empty space can exhibit negative energy under certain conditions. Could this be a hint that the ingredients for stable wormholes exist somewhere in the universe? The possibility that supermassive black holes could hide wormholes isn't just an academic question. It speaks to humanity's deepest yearnings for exploration and discovery. If wormholes exist, they could offer shortcuts across the galaxy, enabling us to visit distant stars and planets within a human lifetime. They might also allow us to peer into other universes, revealing realms governed by entirely different laws of physics. These ideas challenge us to rethink our assumptions about the nature of reality and inspire us to dream of futures we can scarcely imagine. The notion of supermassive black holes concealing wormholes reminds us that the universe is full of surprises, defying our expectations and inspiring us to dream of possibilities beyond the familiar boundaries of our solar system. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if there was a star so strange, so unpredictable, that it defied all explanations? A star whose light dims and flickers in ways no astronomer can fully understand. Welcome to the mystery of Tabby's star, a celestial enigma that has puzzled scientists and sparked imaginations across the globe. Tabby's star, officially known as KIC 8462852, first caught the attention of astronomers through data collected by NASA's Kepler Space Telescope. What made it stand out wasn't its size, temperature, or distance, but how its brightness changed over time. Unlike any other star observed, Tabby's star exhibited irregular and dramatic dips in its light output, sometimes dimming by up to 22%. At first glance, these fluctuations seem random, occurring at unpredictable intervals and varying in intensity. Some dips last for days, while others persist for weeks or longer. No natural phenomenon could easily account for such behavior, leaving researchers baffled. One theory suggests that a massive swarm of comets or dust clouds orbiting the star might be causing the dimming. These objects could pass between the star and Earth, temporarily blocking its light. While plausible, this explanation struggles to fully explain the scale and timing of the dips. Another hypothesis involves debris from a destroyed planet or moon scattered into an irregular disk around the star. Over time, this debris could clump together and drift across our line of sight, creating the erratic patterns observed. Yet, none of these theories have been conclusively proven. Among the more speculative ideas is the possibility of alien megastructures, colossal artificial constructs built by an advanced extraterrestrial civilization. Imagine a structure like a Dyson sphere, designed to harness energy directly from the star. As parts of this hypothetical structure pass in front of the star, they could block its light in irregular ways. While this idea captured public imagination and fueled countless sci-fi stories, subsequent observations ruled out many assets of the alien megastructure hypothesis. For instance, detailed studies found no signs of heat signatures or radio signals that would typically accompany such technology. In recent years, additional research has shed new light on Tabby's star. Astronomers now believe that ordinary interstellar dust may play a significant role in its unusual dimming. Tiny particles unevenly distributed around the star could scatter light in complex ways, producing the baffling pattern seen by Kepler. However, questions remain. Why does the dimming occur at such extreme levels compared to other stars with similar dust clouds? And why do some dips exhibit sharp, sudden drops, followed by equally abrupt recoveries? Each new discovery brings us closer to solving the puzzle, but also deepens the intrigue. The mystery of Tabby's star. isn't just about understanding one peculiar object. It challenges us to rethink what we know about stellar behavior and planetary systems. It reminds us that the universe is full of surprises, pushing the boundaries of our knowledge and sparking curiosity. Whether caused by natural processes or something entirely unforeseen, Tabby's star invites us to embrace the unknown. Its strangeness inspires us to keep looking up, searching for answers amidst the stars. Tabby's star reminds us that the cosmos is vast and filled with mysteries waiting to be unraveled. Its flickering light serves as a beacon, calling us to explore, question, and dream. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the Earth is constantly bombarded by invisible messengers from the farthest reaches of the universe? These are cosmic rays, high-energy particles traveling at nearly the speed of light, carrying secrets from the most violent and mysterious corners of the cosmos. Cosmic rays are not rays at all. They're subatomic particles, such as protons or atomic nuclei, accelerated to unimaginable speeds. Some of these particles carry more energy than anything we can produce in laboratories on Earth. In fact, the highest energy cosmic rays possess energies millions of times greater than those achieved by the Large Hadron Collider, the most powerful particle accelerator ever built. But here's the puzzle. Despite decades of study, scientists still don't know exactly where most cosmic rays originate. Their journey through space erases many clues about their source, leaving us to piece together their story using indirect evidence. Cosmic rays consist mostly of protons, but they also include heavier atomic nuclei, electrons, and even antimatter particles, like positrons. When these high-energy particles collide with Earth's atmosphere, they create cascades of secondary particles, a shower of matter and radiation that rains down on our planet. These collisions have helped us learn about the composition of cosmic rays, but they've also deepened the mystery. For instance, why do some cosmic rays reach Earth with energies so extreme that they defy explanation? One leading theory suggests that cosmic rays are born in the most energetic environments in the universe, places like supernova remnants, black holes, and neutron stars. Supernovae, for example, release colossal amounts of energy when massive stars explode, potentially accelerating particles to cosmic ray energies. Other candidates include active galactic nuclei, the supermassive black holes at the centers of galaxies, and gamma-ray bursts, which are among the brightest events in the universe. However, pinpointing the exact sources has proven incredibly difficult because cosmic rays are deflected by magnetic fields as they travel through space, scrambling their trajectories. The biggest obstacle to solving the cosmic ray mystery is their erratic paths. Unlike light, which travels in straight lines, cosmic rays are charged particles. This means they're bent and twisted by magnetic fields throughout the galaxy and beyond. By the time they reach Earth, their original direction is lost, making it nearly impossible to trace them back to their origins. To overcome this challenge, scientists use indirect methods. For example, neutrinos, ghostly particles produced alongside cosmic rays, travel in straight lines and can reveal the locations of their sources. Similarly, gamma rays emitted during cosmic ray acceleration processes provide valuable hints about the environments where these particles are born. Some cosmic rays are so energetic that they challenge our understanding of physics. Known as ultra-high-energy cosmic rays, these particles pack more punch than anything else in the known universe. To give you a sense of scale, a single proton with this much energy has the kinetic energy of a fastball thrown by a professional baseball pitcher, but compressed into a particle smaller than an atom. How do these particles gain such incredible energies? One possibility is that they're accelerated by shock waves in the aftermath of supernovae, or by the intense gravitational forces near black holes. Another idea is that they come from exotic phenomena, such as decaying dark matter or interactions involving primordial black holes left over from the Big Bang. Cosmic rays are more than just a scientific curiosity. They're messengers from the distant universe, carrying information about the most extreme environments and processes in existence. Understanding their origins could unlock new insights into the nature of matter, energy, and the fundamental forces that govern the cosmos. They also remind us of the dynamic relationship between Earth and the wider universe. Every second, billions of cosmic rays strike our atmosphere, connecting us to the vast expanse of space in ways we're only beginning to understand. The mystery of cosmic rays invites us to marvel at the wonders of the universe, whether they originate from exploding stars, voracious black holes, or something even stranger. They challenge us to keep exploring, questioning, and dreaming. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if, somewhere out there in the vastness of space, there's another Earth, a planet so similar to ours that it could be home to life as we know it? Could such a world exist hidden among the billions of stars and galaxies? For centuries, humans have gazed at the stars and wondered if we're alone in the universe. In recent decades, advances in astronomy have brought us closer than ever to answering that question. Scientists have discovered thousands of exoplanets, planets orbiting other stars, some of which lie within the habitable zone, where conditions might support liquid water and potentially life. But what about a true second Earth, a planet with an atmosphere, oceans, continents, and perhaps even life forms? Could such a world exist undetected in the depths of space? A second Earth would need to share many characteristics with our own planet. It would likely orbit a star similar to the Sun within the habitable zone, the region where temperatures allow for liquid water to exist. It would also need a stable climate, a protective magnetic field, and an atmosphere rich in oxygen or other gases conducive to life. While astronomers have identified promising candidates, none have yet matched all the criteria to be considered a true twin of Earth. But the search is far from over. With billions of stars in the Milky Way alone and countless planets orbiting them, the odds suggest that a second Earth may be out there, waiting to be found. The challenge lies in the sheer scale of the universe. Even with cutting-edge telescopes like Kepler, S, and the James Webb Space Telescope, detecting distant planets is incredibly difficult. Most exoplanets are discovered indirectly, through methods like the transit method, observing dips in a star's brightness as a planet passes in front of it, or radial velocity measurements, which detect wobbles in a star caused by gravitational tugs from orbiting planets. These techniques work best for large planets close to their stars, making smaller Earth-like planets harder to spot. Additionally, confirming whether a planet has an atmosphere or signs of life requires advanced instruments capable of analyzing light reflected or absorbed by the planet, a task that remains on the frontier of modern science. One intriguing possibility is that a second Earth exists much closer to home in our own solar system. While Mars and Europa often steal the spotlight in the search for extraterrestrial life, some scientists speculate that Venus, despite its hellish surface, might harbor microbial life high in its clouds, or perhaps ancient fossils lie buried beneath the icy crusts of moons, like Enceladus or Titan. On the other hand, a second Earth could be lurking in interstellar space, an orphan planet ejected from its original star system, drifting freely through the galaxy. Such rogue planets are thought to outnumber stars, and while they lack sunlight, internal heat from radioactive decay or residual formation energy could sustain subsurface oceans teeming with life. The discovery of a second Earth would be one of the most profound moments in human history. It would confirm that life isn't unique to our planet and offer insights into how common or rare life might be in the universe. If the planet harbors intelligent life, it could revolutionize our understanding of civilization, technology, and our place in the cosmos. Even if the planet is barren, finding a second Earth would provide valuable clues about planetary formation, habitability, and the long-term survival of worlds like ours. It would serve as a reminder that we are part of something far greater than ourselves. The possibility of a second Earth reminds us of the boundless potential of the universe. Whether it's a thriving world filled with life or a quiet, rocky sphere orbiting a distant star, its existence challenges us to keep looking, dreaming, and exploring. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the universe harbors monsters far larger than we ever imagined? Black holes so massive they defy our understanding of how such titanic objects could even form. These are ultra-massive black holes, beasts lurking at the hearts of galaxies, challenging everything we thought we knew about the cosmos. Ultra-massive black holes are not just big, they are unimaginably enormous. While ordinary supermassive black holes can weigh millions or billions of times the mass of our sun. Ultramassive black holes tip the scales at tens of billions of solar masses. Some, like the one in the galaxy Home 15A, may exceed 40 billion solar masses, a number so staggering it's hard to fathom. But here's the puzzle. How do these cosmic giants grow so large? Current theories suggest that black holes grow by consuming matter and merging with other black holes. Yet, the sheer size of ultra-massive black holes raises questions about whether this process alone is enough. One possibility is that ultra-massive black holes started as seeds in the early universe, black holes born from the collapse of massive gas clouds rather than dying stars. These primordial seeds could have been far larger than typical stellar mass black holes, giving them a head start in their growth. Another theory involves rapid accretion, where black holes devour vast amounts of gas and dust at incredible speeds. In the dense environments of galactic cores, this feeding frenzy could accelerate their growth beyond what we once thought possible. But even this explanation struggles to account for the largest examples we've discovered. The existence of ultramassive black holes challenges our understanding of physics. For instance, some appear to be too large to have formed within the age of the universe itself, at least according to current models of black hole evolution. This raises the tantalizing possibility that there's something missing in our knowledge of how black holes grow. Some researchers speculate that these behemoths might be relics of a time before the Big Bang, leftover structures from an earlier universe. Others propose exotic mechanisms, such as direct collapse scenarios or interactions with dark matter, which could fuel their extraordinary growth. Understanding ultramassive black holes isn't just about satisfying scientific curiosity. It's about unraveling the story of the universe itself. These giants play a crucial role in shaping the galaxies they inhabit. Their immense gravity influences star formation, sculpts galactic structures, and drives powerful jets of energy that stretch across millions of light years. They also serve as natural laboratories for testing the limits of general relativity and quantum mechanics. By studying these monstrous objects, we gain insights into the fundamental forces that govern reality. Ultra-massive black holes might also hold answers to other cosmic puzzles. For example, their extreme conditions could shed light on the nature of dark matter. Could dark matter clump around these black holes, providing additional fuel for their growth? Or might they act as anchors, influencing the distribution of galaxies throughout the universe? There's also the question of whether these black holes could hide wormholes or other exotic phenomena. While speculative, the idea captures the imagination. What if these giants are gateways to other parts of the cosmos? The mystery of ultramassive black holes reminds us that the universe is full of wonders that push the boundaries of human understanding. Whether they're ancient relics, products of unimaginable processes, or keys to unlocking deeper truths, they challenge us to dream bigger and explore further. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if there were objects in the universe so dense that a single teaspoon of their material weighed billions of tons? These are neutron stars, cosmic remnants left behind after massive stars explode in supernovae. Their extreme density and mysterious properties challenge everything we know about matter and gravity. Neutron stars are the collapsed cores of massive stars that have gone supernova. When a star much larger than our Sun exhausts its nuclear fuel, it can no longer resist the pull of gravity. Its core collapses under its own weight, crushing protons and electrons together to form neutrons, hence the name neutron star. These stellar remnants pack more mass than our Sun into a sphere just 10 to 20 kilometers across. To put that into perspective, imagine squeezing the entire mass of Mount Everest into a sugar cube. Such density is almost incomprehensible, yet neutron stars exist as some of the densest objects in the universe. The formation of a neutron star begins with a catastrophic event, a supernova explosion. When a massive star runs out of fuel, its outer layers collapse inward at speeds approaching 20 the speed of light. This implosion generates such immense pressure that atomic nuclei themselves are crushed, leaving behind a hyper-dense core made almost entirely of neutrons. Not all collapsing stars become neutron stars, however. If the core's mass exceeds a certain limit, about 3 times that of the Sun, it will continue collapsing into a black hole. But for those that stop short, the result is a neutron star, an object so compact that its surface gravity is hundreds of billions of times stronger than Earth's. Neutron stars are not just incredibly dense, they exhibit other bizarre and extreme properties. For instance, they spin at astonishing speeds, sometimes rotating hundreds of times per second. These rapidly spinning neutron stars, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. Their magnetic fields are equally extraordinary, often trillions of times stronger than Earth's. In fact, magnetars, a subclass of neutron stars, harbor the strongest magnetic fields in the universe. A magnetar's field is so powerful that it could strip information from a credit card located on the moon. One of the greatest mysteries surrounding neutron stars lies within their interiors. At such extreme densities, matter behaves in ways we don't fully understand. Scientists believe that the inner core may consist of exotic states of matter, such as quark-gluon plasma, or even strange quark matter, forms of matter that cannot exist naturally anywhere else in the universe. At the center, pressures are so intense that neutrons might break down entirely, forming a soup of fundamental particles. Unlike anything observed in laboratories, understanding these conditions requires insights from both quantum mechanics and general relativity, two theories that often clash when applied simultaneously. Studying neutron stars helps us unravel the secrets of the universe's most extreme environments. They serve as natural laboratories for testing the limits of physics, particularly the behavior of matter under conditions impossible to replicate on Earth. By observing neutron stars, scientists gained valuable clues about the nature of gravity, the strong nuclear force, and the origins of elements heavier than iron, which are thought to form during neutron star collisions. Moreover, neutron stars remind us of the fragility and resilience of matter itself. Despite being subjected to forces that would obliterate anything else, they persist, balancing precariously between collapsing further into black holes and maintaining their structure. The enigma of neutron stars invites us to marvel at the wonders of the cosmos. Their extreme density, rapid spins, and mysterious interiors challenge our understanding of the universe and push the boundaries of human knowledge. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if humanity has already been contacted by an alien civilization, but we simply didn't recognize it? Could extraterrestrial messages be hiding in plain sight, buried within the vast streams of data collected from space? For decades, scientists have scanned the skies for signs of extraterrestrial intelligence. Projects like SETI, Search for Extraterrestrial Intelligence, use radio telescopes to listen for structured signals that might indicate alien communication. Yet, despite years of effort, no definitive evidence has emerged. But what if the problem isn't their absence? It's our inability to interpret their presence. Imagine receiving a message written in a language so foreign, so advanced, that it looks indistinguishable from random noise. How would we know it was a message at all? If aliens were trying to communicate with us, they wouldn't necessarily use methods familiar to humans. For instance, instead of sending simple radio waves, they might encode information in ways far beyond our current comprehension. They could use quantum entanglement, neutrino beams, gravitational waves, or even dark matter as carriers for their messages. Consider how differently we perceive reality compared to other species on Earth. A dog can hear frequencies we cannot. A mantis shrimp sees colors invisible to human eyes. If aliens perceive the universe through entirely different senses, their attempts to reach out might bypass our detection entirely or appear as something mundane. Every day, observatories around the world collect petabytes of data, radio signals, light patterns, and particle emissions streaming from distant corners of the cosmos. Most of this data is analyzed using algorithms designed to look for specific types of anomalies, such as regularly repeating pulses or narrow band transmissions. But what if alien messages don't fit these criteria? What if they're embedded in seemingly chaotic phenomena like gamma ray bursts, fast radio bursts, or fluctuations in stellar brightness? Without knowing exactly what to look for, we risk overlooking subtle clues hidden among the noise. There are tantalizing examples throughout history where strange signals sparked speculation about alien contact. Take the famous WOW signal detected in 1977, a powerful burst of radio waves from deep space that matched many characteristics expected of an artificial signal. Despite extensive follow-up searches, the source was never identified, leaving its origin unresolved. More recently, astronomers discovered peculiar dimming patterns around Tabby's star, which some hypothesized could be caused by alien megastructures. While later studies suggested natural explanations, the episode highlights how unfamiliar phenomena often trigger debates about extraterrestrial involvement. One reason we might fail to identify alien messages is sheer complexity. Advanced civilizations could operate on timescales incomprehensible to us, encoding messages across millennia rather than seconds. Their languages and technologies might rely on principles we haven't yet discovered or may never discover. Another possibility is that their messages aren't meant for us at all. Just as a dolphin might overhear human conversations without understanding them, we could be intercepting interstellar communications intended for someone else entirely. To uncover hidden alien messages, scientists will need to rethink how they analyze data. Machine learning algorithms capable of identifying complex patterns could help sift through the overwhelming volume of information collected daily. Collaborations between astrophysicists, linguists, mathematicians, and computer scientists may also provide fresh perspectives on decoding potential signals. Additionally, widening the scope of what constitutes a message could yield breakthroughs. Instead of focusing solely on electromagnetic signals, researchers might investigate physical artifacts, gravitational signatures, or even biological markers left behind by visiting probes. The possibility that we've already received alien messages but failed to recognize them is both humbling and exhilarating. It reminds us of the vastness of the unknown and the limits of human perception. Even if we haven't found proof yet, the act of searching expands our horizons and connects us to the infinite possibilities of the cosmos. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the planets orbiting distant stars moved in ways that defy everything we know about gravity and motion? Imagine worlds tracing wildly elliptical paths, swinging close to their stars before retreating into the cold depths of space, or even planets sharing orbits or moving backward against the spin of their star. When astronomers first began discovering exoplanets, planets orbiting other stars, they expected to find systems similar to our own solar system. Planets would follow nearly circular orbits, neatly spaced around their host stars, with smaller rocky worlds closer in and gas giants farther out. But what they found instead was far stranger. Some exoplanets have orbits so eccentric they resemble comets more than planets. Others defy expectations entirely, moving in ways that challenge our understanding of how planetary systems form and evolve. These bizarre orbits raise profound questions about the forces shaping these alien worlds. One of the most striking examples of unusual orbits comes from hot Jupiters, massive gas giants that orbit perilously close to their host stars. In many cases, these planets follow highly elliptical paths, bringing them scorchingly near their stars at one end of their orbit and much farther away at the other. This behavior is baffling because such extreme orbits should be unstable over long periods. Scientists believe these planets may have formed farther out in their systems and migrated inward due to gravitational interactions with other massive bodies. But why didn't they settle into stable, circular orbits like Jupiter in our solar system? Even more puzzling are planets that move in retrograde orbits, traveling in the opposite direction to the rotation of their host star. Normally, planets and stars form together from the same spinning disk of gas and dust, so their motions tend to align. Retrograde orbits suggest something dramatic must have happened, perhaps a violent collision or gravitational tug-of-war with another massive object. Other planets exhibit misaligned orbits, where their orbital planes are tilted sharply relative to the equator of their star. These misalignments hint at chaotic histories, possibly involving nearby passing stars or rogue planets, disrupting the delicate balance of the system. In some cases, multiple planets share the same orbit, a phenomenon known as co-orbital configuration. For example, two planets might occupy the same path around their star, separated by 60 degrees in what's called a Lagrange point. This setup creates a stable dance between the planets, preventing collisions despite their proximity. Trojan worlds, which trail or lead a larger planet in its orbit, are another variation of shared orbital dynamics. While common among asteroids in our solar system, finding Trojans or co-orbital planets elsewhere in the universe adds complexity to our models of planetary formation and stability. Not all exoplanets are bound tightly to their stars. Some wander freely through interstellar space, untethered to any host star, known as rogue planets. These lonely wanderers may have been ejected from their original systems during chaotic gravitational encounters. On the opposite end of the spectrum, some planets remain tethered but orbit at vast distances, taking thousands of years to complete a single trip around their star. These bead orbits pose challenges for detection and raise questions about how such distant planets could form in environments with scarce material. The strange orbits of exoplanets remind us that the universe is far more diverse and dynamic than we imagined. They challenge our assumptions about how planetary systems are born and evolve, pushing us to rethink the rules governing gravity, motion, and celestial mechanics. These discoveries also deepen the search for habitable worlds. Could life exist on a planet with a wildly elliptical orbit, experiencing searing heat followed by freezing cold, or on a world locked in a stable co-orbital relationship with another planet? Each unique orbit expands the possibilities of where and how life might arise. The strange orbits of exoplanets invite us to marvel at the infinite creativity of the cosmos. Whether shaped by chaos, migration, or unseen forces, these alien worlds remind us that there is still so much to learn about the universe we inhabit. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if, hidden in the shadows of craters or beneath layers of dust, there are traces of ancient civilizations or even evidence of modern engineering not made by human hands? Could artificial structures exist on the Moon or Mars, waiting to be discovered? For decades, astronomers, scientists, and conspiracy theorists alike have speculated about the possibility of artificial structures on the Moon and Mars. From strange anomalies seen in satellite images to unusual patterns in the terrain, these celestial bodies have sparked imaginations and debates. While much of what appears mysterious can often be explained by natural geological processes, some features continue to fuel curiosity. Are these just tricks of light and shadow, or could they hint at something far more profound? The Moon has long been a canvas for speculation. Its barren surface is dotted with craters, valleys, and plains that sometimes appear oddly geometric when viewed from certain angles. Some claim these formations resemble ruins of ancient cities, pyramids, or even landing pads for extraterrestrial spacecraft. One famous example is the so-called shard, an elongated object photographed during NASA's Apollo missions. While likely a natural rock formation sharpened by eons of micrometeorite impacts, its shape raises eyebrows among those who dream of lunar mysteries. Another intriguing feature is the monolith, a towering structure spotted in images taken by orbiters. Though geologists suggest it's simply a result of volcanic activity or erosion, its stark rectangular appearance invites wilder interpretations. Mars, with its rust-red deserts and towering volcanoes, offers even more opportunities for speculation. Over the years, high-resolution photographs from rovers and orbiters like NASA's Mars Reconnaissance Orbiter have revealed peculiar shapes and arrangements in the Martian landscape. One of the most famous examples is the Face on Mars, first imaged by the Viking 1 orbiter in 1960. At first glance, it appeared to depict a humanoid face carved into the Cydonia region. Subsequent imaging showed it was merely a mesa shaped by wind and erosion, but not before inspiring countless books, documentaries, and sci-fi stories. Other anomalies include the glass worm, a sinuous ridge covered in reflective material that some believe might be remnants of a glass-like tube system, possibly used for transportation or habitation. Scientists argue it's likely lava flows solidified over time, but the debate persists. If artificial structures do exist on the Moon or Mars, who or what built them? One possibility is that they're relics of an ancient alien civilization, long extinct. Perhaps millions of years ago, intelligent beings visited our solar system and left behind monuments, machines, or markers as part of their legacy. Alternatively, some propose that advanced Earth-based civilizations, either prehistoric humans or lost societies, might have ventured beyond our planet and constructed bases on these nearby worlds. While far-fetched, such ideas tap into humanity's enduring fascination with hidden histories. A third hypothesis involves modern-day visitors, aliens currently observing us from afar, using the Moon or Mars as outposts. If true, these structures would represent evidence of ongoing extraterrestrial activity within our cosmic backyard. Before jumping to conclusions, it's important to consider natural explanations. Many seemingly artificial features can be attributed to pareidolia, the psychological phenomenon where humans perceive familiar patterns like faces or buildings in random stimuli. Additionally, the harsh environments of the Moon and Mars create unique geological formations. Wind erosion, volcanic activity, and meteorite impacts sculpt landscapes in ways that may look unnatural at first glance. Shadows cast by jagged rocks or hills can also create illusions of symmetry or design. Finally, image artifacts caused by camera lenses, lighting conditions, or data compression errors can distort reality, leading to misinterpretations of otherwise ordinary terrain. The search for artificial structures on the Moon and Mars isn't just about proving life exists elsewhere. It's about understanding our place in the universe. Discovering evidence of past or present intelligence outside Earth would redefine how we view ourselves, our history, and our future. It would also open up new avenues for exploration. If artificial structures were found, they could hold technologies, knowledge, or resources invaluable to humanity. Even if no such discoveries are made, the pursuit itself drives innovation and inspires generations to reach for the stars. The idea of artificial structures on the Moon or Mars reminds us that the cosmos is full of possibilities. Whether born from imagination, coincidence, or genuine mystery, these speculations challenge us to keep looking, questioning, and dreaming. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite. What if the night sky isn't as constant as it seems? What if some stars, shining brightly for millennia, suddenly disappear without a trace? Could these missing stars be evidence of extraordinary cosmic phenomena, or something even more mysterious? For centuries, astronomers have mapped the heavens, charting the positions and behaviors of countless stars. But in recent years, scientists have noticed something strange. Some stars simply vanish. These aren't supernovae, explosive stellar deaths that leave behind remnants like neutron stars or black holes. Instead, these stars seem to blink out of existence entirely, leaving no corpse, no debris, and no explanation. How can a star, often billions of times larger than Earth, just disappear? And why does it happen? One possibility is that these missing stars are undergoing a rare and poorly understood process called failed supernovae. In this scenario, a massive star collapses directly into a black hole without producing the brilliant explosion typically associated with its demise. This quiet death would make the star appear to vanish suddenly, as light from the star is abruptly extinguished. While failed supernovae might explain some cases, they don't account for all instances of disappearing stars. Other theories suggest more exotic explanations, such as interactions with dark matter or advanced alien technologies. Some researchers speculate that dark matter, the invisible substance thought to make up most of the universe, could play a role in the disappearance of stars. For example, if a dense clump of dark matter, known as a dark matter halo, were to pass through a star, it could disrupt the delicate balance of forces holding the star together. The result might be a catastrophic collapse or disintegration, causing the star to wink out of sight. This idea remains speculative, but it highlights how much we still don't know about the interplay between ordinary matter and the unseen forces shaping the cosmos. Another tantalizing hypothesis involves intelligent extraterrestrial life. Could vanished stars be scenes of advanced civilizations harnessing stellar energy on a scale beyond our comprehension? Concepts like Dyson spheres, hypothetical megastructures built around stars to capture their energy, suggest that aliens might dismantle or obscure stars for their own purposes. If true, the disappearance of a star could represent the ultimate act of resource extraction, leaving behind only silence where once there was light. Among the leading natural explanations is the concept of failed supernovae. When a massive star exhausts its nuclear fuel, it can no longer resist the inward pull of gravity. Normally, this leads to a supernova, scattering the star's outer layers into space while forming a compact remnant like a neutron star or black hole. However, in some cases, the core collapses so quickly and completely that it forms a black hole without any visible fireworks. This phenomenon has been observed to it indirectly. Astronomers monitoring clusters of stars have noted instances where a luminous blue variable, a type of massive star, suddenly disappears. While exciting, these observations raise further questions about the conditions necessary for such an event. The mystery of vanishing stars challenges our understanding of stellar evolution and the life cycle of stars. By studying these disappearances, scientists hope to uncover new insights into the processes governing the birth, life, and death of stars. These events also remind us of the vastness and unpredictability of the universe. Each vanished star is a reminder that the cosmos is full of surprises, pushing the boundaries of human knowledge and inspiring us to look deeper into the unknown. The disappearance of stars invites us to marvel at the transient beauty of the universe. Whether caused by natural phenomena or influenced by forces beyond our current understanding, these vanishing acts challenge us to dream bigger and explore further. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine and the universe feels just a little more infinite. What if black holes are more than just cosmic vacuum cleaners, swallowing everything that ventures too close? What if these enigmatic giants are gateways to other dimensions, hidden realms beyond the boundaries of our universe? Black holes have long fascinated scientists and dreamers alike. These regions of space-time, where gravity is so intense that not even light can escape, challenge our understanding of the universe. At their centers lies the singularity, a point of infinite density where the laws of physics, as we know them, break down. But what if the singularity isn't the end? What if it's a doorway to another reality, a bridge to other dimensions, or even parallel universes? According to Einstein's theory of general relativity, a black hole warps space-time so severely that it creates a region from which nothing can return, the event horizon. Beyond this boundary lies the singularity, a place where time and space cease to exist as we understand them. Some physicists speculate that instead of destroying matter, the singularity could act as a conduit, funneling objects into another part of the universe, or even into an entirely different dimension. This idea aligns with solutions to Einstein's equations that suggest the existence of wormholes, hypothetical tunnels connecting distant points in space-time. One possibility is that black holes are actually entrances to wormholes. Imagine folding a piece of paper so two distant points touch. A wormhole would act as a shortcut between those points. If black holes serve as one end of such a tunnel, they could provide access to faraway galaxies or even alternate realities. However, for a wormhole to remain stable, it would require exotic matter with negative energy to counteract the crushing force of gravity. While this remains purely theoretical, some researchers believe quantum mechanics might hold clues to the existence of such materials. Quantum mechanics introduces another layer of intrigue. The black hole information paradox, the question of whether information falling into a black hole is lost forever, hints at connections between black holes and other dimensions. One proposed solution is the holographic principle, which suggests that all the information about objects entering a black hole is encoded on its event horizon. But what happens to that information next? Could it be transmitted to another dimension, preserving the integrity of quantum mechanics while seemingly violating classical physics? Another tantalizing idea is that black holes might connect to brains, higher dimensional surfaces predicted by string theory. In this framework, our universe could exist on a three-dimensional brain embedded within a higher dimensional space. Black holes might serve as passages between these brains, allowing travel to realms governed by different physical laws. While speculative, this concept raises profound questions about the nature of reality. Could there be entire universes operating alongside ours, hidden from view until accessed through black holes? The notion of black holes as portals challenges us to rethink the limits of exploration and discovery. If they truly lead to other dimensions, they could unlock secrets about the multiverse, the origins of the cosmos, and the fundamental forces that govern existence. They also remind us of humanity's enduring quest for meaning. Whether black holes are gateways or simply cosmic dead ends, the search for answers inspires us to dream of futures we can scarcely imagine. The idea of black holes as portals invites us to marvel at the wonders of the universe. Whether they're bridges to other worlds or ultimate mysteries yet unsolved, they challenge us to keep looking, questioning, and dreaming. Let this thought lull you deeper into tranquility, knowing that the universe holds wonders far greater than we can comprehend. Let this mystery carry you gently into sleep, where dreams and reality intertwine, and the universe feels just a little more infinite.